For our STAT 1601 final project, we were assigned to find a data set of our choice and provide an analysis of it. And with that, my group and I decided that it would be most interesting to conduct a final experiment on the airline satisfaction ratings. So we discovered that there were so many different factors that would be taken into account, such as the ease of travel, arrival time, departure time, whether there's Wi Fi, and so many other factors that played a part into these satisfaction ratings. So let's get right into it.
For our STAT 1601 final project, we analyzed airline satisfaction ratings. Our chosen data set contains the results to a survey from an undisclosed airline. Some variables our data set include age, gender, and travel type, but the majority of our data comes from airline satisfaction ratings that are on a scale of 1 to 5 and include satisfied and neutral/dissatisfied ratings.
Hi, so for motivation, the airline industry is obviously a super important part of globalization. Taking flights to other parts of the world has become easier than ever, with many individuals utilizing airlines for business trips and personal travel. As airlines recover from the effects of COVID, it's important to understand what factors are good, because many people turned away from air travel during COVID because the airlines went down. So we thought it'd be interesting to look at the various factors that lead to comfort, whether it's the ease of booking or the several amenities that are provided to customers while on the journey. In addition, we also have the chance to see if the demographics of customers have any connection to how they judge certain factors related to air travel.
So next, we're going to look into relevant variables. So much of the data included in the data set is comprised of responses to a survey in which customers were asked to rate several different features of their flight. And these include in-flight Wi-Fi, convenient scheduling, ease of online booking, gate location, food and drink, quality of online boarding, seat comfort, in-flight entertainment, quality of onboard service, amount of legroom, handling of baggage, quality of check-in service, service while in flight, and cleanliness. So these such variables related to details about the customers are present. And age, gender, type of customer, purpose of flight, and flight distance must also be taken into account.
So moving on to our data preparation. First, we summarize the numeric variables in our data set, including discrete and continuous variables. These summaries for the particular variables in the data set itself include the minimum, median, mean, first quartile, third quartile, and maximum values in the variables themselves. For example, we can take a look at that the average or mean age for the flights was 39.62 years. Then we included a measure of spread or ranges of some key variables in our data set, including the age, range of flight distances, and scores, in which 6 rating categories were chosen to get a maximum total of 30 points. It's incredibly interesting to see from the data set that people will even fly just for 31 miles to get to their preferred destination.
When it comes to how we clean the data set in order to prepare it for analysis, we have removals, additions, filtering and subsetting, and miscellaneous changes. For the removals, we removed the X column, which acted as a counter for the data set. It's not necessary because R already has a built-in counter for the observation numbers. The ID column, which kept track of customer ID numbers, will have no use with data analysis, so that was also removed as well. When it comes to the additions, we added 2 columns. One that summed up the departure and arrival delays for each observation, giving us a total for the delay in minutes, and 6 of the ratings variables, specifically the in-flight Wi-Fi service, the convenience of the departure and arrival times, the ease of online booking, the gate location, food and drink, and online boarding, were summed up to create a variable called total score that kept track of a score out of 30. When it comes to filtering and subsetting, all observations which featured ratings, distances, and delays equal to 0 were filtered out. In the case of ratings, a 0 counts as an NA value and as such can be filtered out. Distances and delays equal to 0 were filtered out to keep data analysis clean so that the graphs and the other set types of data analysis look smooth. And for the miscellaneous changes, we focused on capitalization and spacing that needed to be corrected as necessary. This is a look at what the data set looked like before and after. You could see the changes that were mentioned in the previous slide.
We also constructed frequency tables of categorical variables, including in-flight Wi-Fi service, ease of online booking, gate location, and food and drink. At first glance, it seems like these variables are numeric, but the fact that there are rankings of 1 through 5 show that they're separate categories. For example, imagine if each ranking 1 through 5 was 1 being poor, 3 being average, and 5 being excellent. Additionally, these rankings of 1 through 5 take a finite number of distinct values, which further proves that they're categorical. Moving on, we also created two-way tables for categorical variables. For example, we made a two-way table displaying the relationship between gender and satisfaction. In this graph, you can tell how many females and males are satisfied and dissatisfied with their experience with the airline. We also made a table showing a customer's type of travel relates to satisfaction levels. You can tell from this graph that only 2 disloyal customers were traveling for personal reasons. It's concluded from the table that if you want to fly for personal reasons, you're more likely to be a loyal customer.
So we're going to start the data visualization section with some bar graphs. On the left-hand side, we have the effect of departure delay on satisfaction. And on the right-hand side, we have the effect of arrival delay on satisfaction. Because departure delay and arrival delay are generally around the same, that's why the graphs are shaped pretty similarly and they look pretty similar. So on the x-axis on the left, we have departure delay in minutes, and on the right x-axis, we have arrival delay in minutes. On both of the y-axes have a number of respondents, and that's why you see the graph generally decreasing because more people have responded with a lower departure delay. So we have a stacked bar graph here with satisfied being in blue and neutral/dissatisfied being in red.
So next, we're going to take a look at the histogram, which looks at customer ages, or rather the distribution of customer ages. So on the y-axis, we have the number of customers, and on the x-axis, we have the age of customers. So we can see on this particular histogram that a cluster of data clumps up around middle-aged customers. So around age of 40, there's the most number of customers that responded, whereas for the younger customers as well as the older customers, the number of customers decreases.
So here we have some box plots, the scores based on gender. On the left side, we have female, and on the right side, we have male. And the box plots are representing the total scores for each gender. So as we can see, the medians both look the same. The inner quartile range is what the box is, and that's going to be slightly larger for the female because the 75th percentile line is a little higher for the females than it is for the males. The 25th percentile looks the same, but yeah, these are the box plots.
For our scatter plot, we represented a relationship between delays. So based on the scatter plot, it shows an overall strong positive linear correlation between arrival and departure delay. And this makes sense logically because as planes that depart later will usually arrive later.
So for the next part of our data visualization, we decided to go with the bubble plot that would look at the delay, flight distance, as well as the satisfaction. So on the y-axis is the flight distance, and on the x-axis, it will be the total delay in minutes. And on the right, we have a key for the score. So the larger the triangle, the higher the score is, and the satisfaction differentiates based on the color of the triangle on the bubble plot, whether they're neutral or dissatisfied, or rather if they were satisfied. So this particular bubble plot just shows the variation in data as it clusters around when the flights are shorter distances rather than longer distances, and then the data set becomes a lot less predictable.
We have some violin plots that show the relationship between flight distance in the class. The three classes are business, economy, and economy plus. For all three classes, you're most likely to choose a flight around 400 in general miles. But as we can see with business, it's like a lot more spread out. It's not as clumped under 1,000 as it is for economy and economy plus.
Moving on to the regression section, our first part is the simple linear regression model. We made two models for this, one that had a predictor of age in years and a response and total score, whereas the second model took the total delay in minutes with the same response of score. The prediction for the first model was 60 years and the response was 18 points, and the prediction for the second model was 60 minutes and the response was approximately 18 minutes. Moving into the analysis, we notice that for every additional unit of a customer's age, there's a 0.025419 increase in the score based on how the customer provided ratings. If we look at the multiple R-squared value, which is 0.006485, that means only 0.64% of the variability in the score can be attributed to the age of a customer. That means age is not a reliable predictor at all. With the second model, we have an even worse situation where there's a decrease 0.003395 in the score. The multiple R-squared value of 5.46 times 10 to the negative 5 means that only 0.00546% of the variability in the score can be attributed to the total delay. This is an even worse predictor of score. Moving on to logistic regression, we made one model, took the predictors of age, flight distance, total score, and total delay, and we tried to get their binary response of either satisfied or neutral/dissatisfied. For the predictions, we took an age of 40, a flight distance of 1,000, a total score of 30, which is the perfect score, and a total delay of 10 minutes. The response is satisfied. Moving on to the analysis, we noticed that we can split the variables into what increase the odds and what decrease the odds. With every additional unit of a customer's age, the chance of a satisfactory rating increases by 2.2%. This means that the older customers, the more likely they're going to be satisfied. With every additional unit of flight distance, the chance of a satisfactory rating increases by 0.07%. This is a very small increase in the odds, which means flight distance doesn't have much of a role to play. We notice that the biggest role in increasing the odds is the score. With every additional unit of score, the chance of a satisfactory rating increases by 16%. The only variable that decreased the odds in our model was the delay, with the chance of satisfactory rating decreasing by 0.01%, which makes sense because if you have a delay, you're more likely to be dissatisfied. If we made a follow-up prediction based on these statistics, we would notice that a prediction with the lowest score should result in a neutral/dissatisfied rating, which it did. Finally, we have the classification section. We made two k-nearest neighbor models for this section. The first one took the total score, the gender of the passenger, which is male or female, the travel type, which is business or personal, and the class, eco, eco plus, or business, eco and eco plus corresponding to economy and economy plus. We wanted to see whether the neighbors would determine whether a customer is loyal or disloyal. So if you put in a score of 20, a gender of male, a travel type of personal, and a class of eco plus, we get a response of a loyal customer. In this case, we see that the k-nearest neighbor model was most accurate when dealing with 5 neighbors, as evidenced by this graph that shows with 5 neighbors, the accuracy was about 85%. With our second model, we took the predictors of flight distance, customer type, and total delay, and wanted to see what the class of customer was. So with the flight distance of 500, a customer type of loyal, and a total delay of 70 minutes, we got a response of economy. In this case, the k-nearest neighbor model was most accurate when dealing with 9 neighbors, meaning that there's probably more data clustered around this particular model to allow it to get an even better distribution. Here are references, and that's the end of the presentation.
That wraps up our presentation on the analysis of airline satisfaction ratings. And through the dataset overview, the motivation, relevant variables, our data visualization, as well as the logistics, I hope that with this newfound information, and newfound knowledge. I hope that you take them into account when you plan your next trip. And with that, that wraps up the year. And I just wanted to thank you for an amazing year, Professor Prince, as well as my group and I. And other than that, that just sums it up. Thank you.